Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So far we have seen various schemes for MIMO transmission and reception. We have seen the zero forcing receiver, we have seen transmit beam forming, Alamuti code. Let us now look at a slightly different perspective on MIMO, which is first let us look at a unique decomposition of the MIMO wireless channel. This is known as the SVD, or the singular value decomposition. So what we are going to look at starting in this module is what is known as the SVD, and this stands for the singular value singular value decomposition. And what this is very useful in characterizing or analyzing the behavior, gaining valuable insights, analyzing behavior or characterizing the MIMO channel. And what is this? This is a decomposition. The singular value decomposition is a decomposition of the channel matrix. Just like we have the eigenvalue decomposition, this is another decomposition for the MIMO channel matrix. But eigenvalue decomposition exists only for square matrices, right? But the singular value decomposition is a general decomposition and exists also for non-square matrices. And therefore, this can be used to gain valuable insights into the properties and behavior of the appropriate underlying MIMO channel. Okay. So, let us start with a brief illustration of the singular value decomposition. So, let us consider the channel matrix H, which is an R cross T. This is an R cross T. This is an R cross T channel matrix, and this has R rows and T columns, and this H, this channel matrix H can be decomposed as H is equal to the product of three matrices U, sigma, V Hermitian, where U is the matrix which contains T columns, U1 bar, U2 bar, so on up to UT bar, correct, times. So, this is the matrix U, which is an R cross T. So, this is an R cross T matrix multiplied by the matrix sigma, which is a diagonal matrix, also termed as the diagonal matrix of the singular values, followed by the matrix V Hermitian, which contains the rows V1 bar Hermitian, V2 bar Hermitian, so on Vt bar Hermitian. So, this sigma, this is our T cross T matrix and the V Hermitian, and therefore, V are also T cross T matrices. So, I am decomposing this as a product of three matrices U, which is an R cross T matrix and contains T columns U1 bar, U2 bar, Ut bar, a diagonal matrix sigma of the singular values sigma 1, sigma 2, sigma t, and a matrix V Hermitian, which contains T rows V1 bar Hermitian, V2 bar Hermitian, so on up to Vt bar Hermitian. And the different matrices, the properties of the different matrices are as follows. So, I have the columns U1 bar Hermitian, Ui bar Hermitian, Uj bar equals 0 if I is not equal to j. If I is equal to j, I have more norm of Ui square, Ui bar Hermitian, Ui is norm of Ui square is equal to 1. So, this property can be summarized as follows: Ui bar Hermitian Uj equals 1 if I is equal to j, 0 if I not equal to j. Therefore, the columns ui, this property is designated as stated as follows: the columns ui bar are ortho, the columns ui bar are orthonormal. So, these columns are orthonormal. Okay. Now, that means if I look at this matrix U Hermitian U, that is equal to U1 bar Hermitian, U2 bar Hermitian, UT bar Hermitian times U1 bar, U2 bar up to UT bar, which is equal to the matrix. Well, what is this matrix? U1 bar Hermitian U1, which is norm of U1 bar square, norm U2 bar square, so on, norm UT bar square, and the diagonal entries are U1 bar Hermitian U2, U2 bar Hermitian U1 bar, and so on. And you can see that the diagonal, so you can see that in this matrix, you can see in this matrix that all the off diagonal elements, so the diagonal elements which are the norm ui square, these are 1, all the off diagonal elements, so these elements, these are zeros. So, therefore, this matrix is a diagonal matrix of ones, and this is therefore the T cross T identity matrix, correct. So, what we have is the first property, we have that U Hermitian U, the matrix is T cross T identity matrix, because this matrix U contains orthonormal columns. Okay. So, we have the first property, that is the matrix U Hermitian U is the T cross T identity matrix. Now, let us look at the matrix V. The matrix V also obeys similar property. So, the matrix V is such that V Hermitian V equals V Hermitian equals the T cross T identity matrix, and this matrix V is a, therefore, this is also known as a unitary matrix. This matrix V is known as a unitary matrix. Now, let us look at the matrix sigma. The matrix sigma, which is the matrix of singular values. Remember, sigma is the diagonal matrix of singular values. This matrix is such that all the singular values are greater than 0, that is, they are non-negative. So, singular values are non-negative. And also importantly, the singular values are arranged in decreasing order of magnitude. So, basically this says that the singular values are arranged in decreasing order of magnitude. The singular values are arranged in decreasing order of magnitude. So, to summarize basically for the singular value decomposition, what are the properties of the singular value decomposition? If you have to summarize them in a nutshell, a channel matrix R cross T channel matrix H with R greater than or equal to T correct, can be decomposed as the product of T3 matrices, that is U, sigma, V, Hermitian, where U is a matrix, is an R cross T matrix which contains orthonormal columns such that U Hermitian U is identity. V is a unitary matrix such that V Hermitian V equals VV Hermitian is identity, and sigma is a diagonal matrix of singular values which are non-negative, and the singular values are arranged in decreasing order. Also, an interesting property of the singular values is that the number of non-negative singular values denotes the rank of the matrix. So, the number of non-zero singular values denotes the rank of the matrix. Okay. So, number of non-zero singular values non-zero singular values is equal to the rank of the matrix. And also let me clearly write this again here, that this singular value decomposition is valid for R greater than or equal to T. That is, the singular value decomposition that we have just described is valid for R is greater than or equal to T. Let us look at some simple examples to understand this thing. So, examples of SVD or the singular value decomposition example. So, let us start with a very simple example. The first case, let us start with this simple example, H is equal to 1 cross 1. This is a basically 2 cross 1 MIMO channel. In fact, this is a single input multiple output or a CMO channel. Basically, we have R equal to 2 and T is equal to 1, correct. So, I have the single input multiple output channel 2 cross 1 channel 1 1. I can write this now as basically 1 over root 2. I can normalize this vector to have unit norm 1 over root 2 1 over root 2 times the T cross T, that is 1 cross 1 matrix root 2 times the 1 cross 1 identity matrix, that is 1. So, now look at this, I have my matrix U which is 2 cross 1, which obeys the property U Hermitian U equals in fact 1, which is the 1 cross 1 identity. I have the diagonal matrix of singular values sigma, which is a 1 cross 1, and root 2 sigma 1 equals square root of 2, which is greater than 0. So, the singular value is greater than 0. My matrix V is simply the trivial matrix that contains 1, and therefore, V Hermitian V equals VV Hermitian equals identity, that is 1 cross 1. It is the 1 cross 1 identity which is equal to 1. So, we have looked at a simple case of a singular value decomposition of a single input multiple output channel in which both the coefficients are 1. I have said that this can be decomposed as the matrix U, which is the 2 cross 1 matrix containing the elements 1 over square root of 2, 1 over square root of 2, correct. Naturally, its column is orthonormal. In this case, there is only one column, so it is normal, that is normalized to unit norm. The singular value is square root of 2, which is greater than 0, times the matrix V, which is again the trivial matrix 1 for this scenario. Okay. So, that explains, that is a simple example of a singular value decomposition. Let us look at a slightly more interesting example. Let us look at a slightly more interesting example of the singular value decomposition. I have the channel matrix H, which is 1 0 0 comma square root of 5. Now, this already is a diagonal matrix, so one might be tempted to conclude that H equals, if I write it in terms of this identity matrices 1 0 0 1 1 0 0 square root of 5 times 1 0 0 1, one might be tempted to conclude that this is a singular value decomposition. This is my matrix U, this is my matrix sigma, this is my matrix V Hermitian. It satisfies all the properties of singular value decomposition, except now look at this, I have sigma 1 equals 1, sigma 2 equals square root of 5. Therefore, sigma 1 is less than sigma 2, and this condition violates the SVD condition or the SVD property, because remember the singular values have to be arranged in descending order of magnitude, or in other words sigma 1 has to be greater than sigma 2. However, here sigma 1 in this decomposition, sigma 1 is less than sigma 2, correct. All the other properties are satisfied, that is I have U Hermitian U is identity because U is the identity matrix, V Hermitian V equals VV Hermitian is also identity, the singular values are positive except the singular values are not arranged in the descending order. Therefore, we have to rectify this since this is not a valid SVD. So, what I want to say is that this is not a valid SVD. Then how do we decompose this singular value decomposition? I have H is equal to 0, I have H is equal to 1 0 0 square root of 5. I can decompose this as follows. I can decompose this as I can first switch the rows of H. So, I can to switch the rows of H, I can multiply it with this matrix which toggles the rows of H. This is the 0 1 1 0, this is the flipped identity matrix, and you can see that flips the rows of H. So, therefore, I can write H is equal to 0 1 1 0 matrix times the 0 square root of 5 1 comma 0. Now, I can flip the columns of this by multiplying the same matrix on the right. I can flip the columns of this by multiplying this same matrix 0 1 1 0 matrix on the right. And now, if you look at this, if I call this my matrix U, if I call this my matrix sigma, if I call this my matrix V, I have U Hermitian U equals identity, V Hermitian V equals V V Hermitian equals identity, and the two singular values are sigma 1 equals square root of 5, sigma 2 equals 1, and I have sigma 1 greater than sigma 2. Therefore, yes, this is a valid. So, this is a valid singular value decomposition. So, what we have done is we have done a simple manipulation. We have pre-multiplied and post-multiplied this by this 1 0 1 1 0 matrix, which is the flipped identity matrix, that basically shuffles these singular values square root of 5 and 1 to the correct order. So, that now we have sigma 1 equals square root of 5, sigma 2 equals 1, and therefore, sigma 1 is greater than sigma 2, both these singular values are positive, and therefore, this is the valid singular value decomposition. And also, of course, these matrices U and V satisfy the properties, namely U Hermitian U is identity, V Hermitian V, V V Hermitian is also identity, therefore, V is a unitary matrix. Okay, fine. So, now let us look at a slightly more refined example. Let us look at a third example of another singular value decomposition. This is a slightly more advanced example of a singular value decomposition. That is, I have H is equal to 1 comma 1, 2 comma minus 2. This is my channel matrix. And therefore, I can write this channel matrix H as first I can write this in terms of two columns 1 comma 1, 1 comma minus 1 times a diagonal matrix 1 comma 0, 0 comma 2. But if these are my singular values, again you can see these are not in the correct order, because one singular value, the 1 is less than 2. Therefore, I will again shuffle these. So, I will shuffle these columns 1 comma minus 1, 1 minus 1, 1 1, and simultaneously I will shuffle the rows of this matrix 0 2 1 0, and now I have the singular values, except this is the flipped diagonal matrix. Therefore, I will shuffle the columns of this by post multiplying by our flipped identity matrix. So, I am going to have, what I am going to have here are 2 comma 0 0 comma 1, and this is basically my flipped identity matrix. And now you can see I have, now you can see I still do not satisfy my property of singular value decomposition, because this U matrix does not contain orthonormal rows, correct, orthonormal columns. So, for this purpose what I am going to do is I am going to normalize the columns of this U matrix. So, I have, so far I have H is equal to 1 minus 1 1 1 times 2 1 0 0, and this is 0 1 1 0, and now you can see I can divide by square root of 2. So, I can divide each column here by square root of 2 to normalize these columns, and this square root of 2 I can multiply here in this diagonal matrix, and now you can see I have, well, now you can see I have the matrix U, I have the matrix sigma, I have the matrix V Hermitian, with U Hermitian U equals identity, U Hermitian U equals identity, V Hermitian V equals VV Hermitian equals also the identity. The two singular values are sigma 1 equals 2 square root of 2, sigma 2 equals square root of 2. Both the singular values are greater than 0, and I have sigma 1 is greater than sigma 2, that is the two singular values are arranged in descending order. Therefore, once again this satisfies all the properties of the singular value decomposition. Therefore, this is a valid singular value decomposition. Okay. So, what we have done in this module is we have defined a new decomposition for the MIMO channel matrix, that is a singular value decomposition. We have defined the various components or the various component matrices of this singular value decomposition, namely the matrices U, sigma, V, and we have illustrated the singular value decomposition using some simple examples, and that comprehensively clarifies this concept of singular value decomposition. Now, the application of singular value decomposition is something that we are going to look at in the subsequent module. Okay. Let us conclude this module here. Thank you very much.